So today's class, I want to take time discussing about electric field lines. Electric field lines, or we say electric lines of force. Electric lines of force. Okay, so we discuss electric field lines or electric lines of force. So what does this mean? Okay. Now consider a positive charge plus Q. Okay. Then we have I have mentioned in the previous class that for a positive charge, the electric field, okay, the electric field lines is directed radially outwards. The electric field lines is directed radially outwards. That's what Faraday told us. And for a negative charge, say minus Q, the electric lines of force is directed radially inwards. It acts inwards. So the electric lines of force, the electric field lines, it originates from a positive charge and it terminates on a negative charge. Okay, this is the direction of the electric field. The direction of the electric field acts outwards for a positive charge, and for a negative charge it acts radially inwards. Okay, now Faraday said that, now suppose you consider a positive charge plus Q. Now this is how he represented the electric field lines for a positive charge. This is how he represented in pictures, pictorially. Okay, picture representation. So this is how he drew the electric field lines. Like this, like this, like this, like this, like this. Similarly, okay, I'll explain to you what I am drawing here. What do you notice through this arrow? Faraday said like this. Okay, just consider a positive charge plus Q. Then Faraday says that the arrowheads represents the direction of the electric field. Okay, the arrowhead is pointing outwards, so the electric field for a positive charge will it be in outward direction. Okay, the arrowheads represents the direction of the electric field, and the length of the arrow represents the magnitude of the electric field. So as you move away from the charge, the magnitude of electric field decreases. As you move closer towards the charge, is it okay? Since the length of the arrow is longest nearer to the charge, right? So as you move closer towards the charge, the magnitude of electric field increases. And as you go away from the charge, the magnitude of electric field decreases. It doesn't become zero. This extends up. It doesn't mean that since the length of the arrow is decreasing, so at infinity there will be no more arrows. It's not like that. It extends up to infinity. Okay, it extends up to infinity, but the magnitude is very small. Okay, it will tend to zero, almost zero, but it doesn't vanish. Is it okay? So electric field due to a charge, due to a source charge plus Q or minus Q, it extends till infinity. Is it okay? Except that its magnitude will be very, 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 very small. Maybe almost negligible at infinity. Are you getting me? So this is how he represented, okay? This is how Faraday represented the electric field lines. Are you getting me? Arrowheads represents the direction of the electric field. And the length of the arrow represents the magnitude of the electric field. But this representation had some problem with the magnitude. So he changed it again. Is it okay? Now we will see that. Similarly, for a negative charge also we can draw. For a negative charge, consider a negative charge minus Q. Actually, we are going in so much deep concept now, okay? This was necessary for you to know, so we are getting much more in detail. For a negative charge, the electric field is directed radially inwards, right? So the arrowhead will point towards the source charge. As you move away from the source charge, the length of the arrow will start to decrease. But it does not vanish. Okay? It extends up to infinity, but the thing is that its magnitude becomes very small. Okay? Again, I'm going to, this is how I can draw, right? Okay? It will become dot, 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 as you go up to infinity. No? Similarly, I can draw as much. Here I have drawn 4 field lines. I can draw 8, I can draw 16. Okay? I can draw 32. So this is how Faraday represented it first. Direction of the arrow gives you the direction of the electric field, and the length of the arrow gives you the magnitude of the electric field. But this representation had some issue, had some problem on finding the magnitude. So finally, he replaced this dotted arrows, okay, in this form. This is how Faraday concluded. Suppose this is your source charge, a positive source charge plus Q, a charge plus Q. Then we know that the direction, the electric field acts radially outwards, right, for a positive charge. So this is how he represented now. See, this is how he represented. The direction will be same. The direction of the arrowhead will give you the direction of the electric field. Direction, he didn't change the direction, because in the first case also there was no issue with the direction. So the arrowhead gives the direction of the electric field, but the dotted arrows, now the increasing or decreasing length of the arrows is now replaced by single line arrow. Is it okay? See? So this time he concluded that the magnitude of the electric field depends upon the density of the field lines. These are your field lines. It depends upon the density of the field lines, meaning, okay, I can draw more as much as I want, okay? Suppose I can draw another field line here, I can draw another field line here, I can draw another field line over here, I can draw another field line over here. So the magnitude of the field, electric field, depends upon the density of field lines. See, closer to the charge, the distance between the lines are very less. The lines are very close to each other, nearer to this charge right now. When you see the lines closer to this charge, is it okay? So these field lines closer to the charge, okay, when they are closest to the charge, the distance between the lines are very, very small. The distance between the lines are very small. Distance between the lines are very small means density of the lines is more, right? Lines are very close to each other, so the density of the lines is more. Is it okay? And as the density of the lines are more the magnitude of the electric field. And as you move away from the charge, distance between the line increases. Distance between these field lines are increasing. So as the distance between the lines are increasing, density of the lines decreases. Now, closer to the charge, okay, the lines are very close to each other. Okay, the lines are very close to each other. So as more the number of lines means more the density, more will be the magnitude. But as you go away from the charge, the distance between the lines increases. So very less density of the lines here. In that case, the magnitude of electric field decreases. So finally, he concluded that, okay, the arrowheads represents the direction of the electric field, and the density of the lines gives you the magnitude of the electric field. Is it all right? Yes. So this is the final conclusion of Faraday. Similarly, for a negative charge, if you are considering a negative charge, then the electric field lines acts radially inwards. So direction will be same as that of the first case. Okay, arrowheads represents the direction of the field, electric field. Now, closer to the charge, the distance between these lines, okay, the distance between the lines are very less. So the lines are closely spaced. So more the density of the lines, more will be the magnitude of the charge. As you go away from the charge, distance between the lines increases. Okay, so the density of the lines decreases. Okay, so in that case, the magnitude of the electric field also decreases. Is it okay? Now, how are you going to define this electric field line? Electric field line can be defined as a path, in which a free positive charge would move if it is allowed to do so. I'll show you in the figure. So suppose this is your charge. I'm going to draw the field lines. For a positive charge, the electric field lines acts radially outwards, right? Okay. Now, suppose you consider a free positive charge. Free positive charge means I'm talking about an imaginary charge known as test charge. Test charge means, yeah, a negligible small positive charge Q naught. We can consider this as a free charge. You take this free charge and place it over here. Where will it go? It will go in this direction. It will go along this line. So this is your electric lines of force. This is your electric field lines. You place this charge, that free charge, free positive charge, and place it over here. Then this charge, this free charge will not go in this direction. It will not go in this direction. Neither it will go in this direction, right? It will just follow this path along this direction. Electric field lines. Okay? So electric field line is a path along which a free positive charge, say your test charge Q naught, would move if it is allowed to do so. Is it okay? Ito test charge loige na ide kunba chaka de rakhibe na. Tai either itu line follow koribo, itu laga path follow koribo, nohele itu laga path follow koribo, nohele itu laga path follow koribo. It will either follow this line, either follow this line, it will either follow this line, or it will either follow this line. It will not follow any other line. It will not follow any other path. So the path that is being followed, the direction that is being followed by this free charge Q naught is known as your electric field lines. That is how you are going to write in the examination. Okay? What is electric lines of force, or what is electric field line? An electric field line is a path along which a free positive charge would move if it is allowed to do so. Similarly, for a negative charge also we can draw, right? Okay? Yes. Any confusion? Okay. Actually, if it was in the classroom, then these things would have not been taught because we need to rush for the syllabus. Okay, but we are not rushing for the syllabus here. So all these concepts needs to be learned, okay? Now properties. Properties of electric field. There are so many properties, okay, but I will be teaching you maybe around 9 or 10 properties, maybe 10, okay? There can be like, I think there are 13 or 14 properties. The first property is, we already understood the first property when we are having an introduction on electric field lines. First property is, the electric field lines originates from a positive charge and terminates on a negative charge. So for a positive charge, the electric field lines originates. No? And for a negative charge, the electric field lines terminates. Is it okay? When you are keeping a positive charge over here and negative charge over here, what will happen? The electric field line will originate from the positive charge and terminate on the negative charge. Is it okay? Yes. So that is the first property. The second property, okay, let me say they means the electric field lines, they originate from a positive charge, and terminates on a negative charge. Terminates on a negative charge. Number 2, they do not form closed loop. They do not form closed loop. What is the meaning of this closed loop? We have seen that from point 1, they originate from the positive charge, they terminate from the negative charge. I'm going to draw a figure according to that. So this is your positive charge plus Q. This is your negative charge minus Q. Electric field line originates from positive charge, goes from positive charge towards negative charge. It originates from positive charge and it will enter the negative charge. But this field line will not come back. Once it originates from the positive charge, then it will terminate. Terminate. Is it okay? It will terminate on the negative charge, and these lines of force will not come back again. Is it okay? That is why they do not form a closed loop. Magnetic field lines, they form a closed loop. Magnetic field lines, they form a closed loop, you see. This is your bar magnet. This is your North Pole, this is your South Pole. The magnetic field lines originates from the North Pole and goes towards the South Pole, right? Inside the magnet again, from the South Pole, it will go to the North Pole. Inside the magnet. So this, they form a closed loop here. But for electric field, they do not form any closed loop. Okay. Point number 3. They do not vanish. Vanish now. V-A-N-I-S. They do not vanish even at infinity. Even at infinity. As you go away from the charge, the magnitude of the field line will decrease. You keep on increasing the distance. The magnitude of the field will keep on decreasing. But to infinity also, it will not be there. It will not vanish. Those field lines will not vanish. So if the field lines do not vanish, then the magnitude will not be 0. Okay, it may be like very, very close to 0, tending to 0, 10 to the power minus 31, 10 to the power minus 100, 10 to the power minus, okay, 1000. But it will not vanish. Alright. The fourth property, I'll wrap this out. The fourth property, the field lines, the number of field lines is subjective, but the density of field lines is objective. What does that mean? The number of field lines are subjective. This is the fourth point, right? the number of field lines, electric field lines, are subjective. I'll tell you an example. Subjective, not subject, subjective. But the density of field lines are objective. Is it okay? Yes. The number of field lines are subjective, meaning the number of electric lines of force depends upon the charge. Okay? Suppose consider any charge, it can give only 4 field lines, whereas for another charge it may give 8 field lines. It doesn't mean that 8 field line is correct and 4 field lines are incorrect. It doesn't mean that. It can have only 2 field lines, it can have 4 field lines, it can have 8 field lines. So subjective. Okay? Nijo kushi azi. No. Suppose itu charge pra charta field line station. Itu charge pra. And this charge gives you 8 field lines. Okay? This charge gives you 8 field lines. It doesn't mean that this is correct and this is incorrect. No, it's not like that. Both are correct. Is it okay? So the number of field lines is subjective. But the density of field lines are objective. Meaning, closer to the charge, in this case, see, the space between the lines are less. So the density is more. As you move away from the charge, the density of the lines decreases. Right? Same here. Okay? At this position, closer to the charge, the field lines are closer to each other. But as you move away, in both the cases, as you move away, the density of the lines decreases. Right? Is it true in both the cases? So the field lines are, or density of field lines are objective. Is it okay? Yes. The next property is the number of field lines is directly proportional to the magnitude of the electric field. Means more the number of field lines, more the magnitude of the electric field. Is it okay? So the fifth property is the number of field lines is directly proportional. I'll show you an example. Is directly proportional to the magnitude of the electric field. Is it okay? Example. Suppose you have a charge plus Q, and this plus Q generates 4 field lines, 4 electric field lines. Okay? You double the magnitude. This is plus Q, right? You double the magnitude. Plus 2Q. Now, then it will generate how many field lines? Here it was 4. Charge is doubled, so it will generate 8 field lines now. Are you getting me? So 1, 2, 3, 4, 5, 6, 7, and 8. So the number of field lines is directly proportional to the magnitude of electric field. If you again double the charge, then it will generate how many field lines now? 16 field lines. If you double the charge again, 8Q plus 8Q, then the electric field lines, then it will generate 32. If you double it 16, then it will generate 64 field lines. Are you getting me? Yes. So the number of electric field lines is directly proportional to the magnitude of the electric field. Okay. The sixth one, the density of the field lines, gives the magnitude of the electric field. Okay? Density of field lines gives the magnitude of electric field. Meaning, at any point or at any region, wherever the density of the lines are more, the magnitude of the field will also be more. But at any region or at any point, if the density of the lines are less, means if the lines are more spaced, okay, then in that case, the magnitude of the field will also decrease. Is it okay? Are you getting me? So the density of the field lines gives the magnitude of the electric field. So this will be which property? Sixth. So the density of field lines gives you the magnitude, of electric field. But these field lines are imaginary, okay? Nah? It doesn't mean that you place a charge here, or then you can see some lines originating from it. You cannot see them. But you can feel its effect. Okay? And its effect acts along these lines. Are you getting me? No? So these are just imaginary lines, okay? Yeah. Table data charge field lines. Is it okay? You cannot see magnetic field lines, you cannot see, but you can like experience it, right? You just place a bar magnet and put some iron fillings above it. Then the iron fillings will arrange themselves. Okay? Then the magnetic field lines will be visible, no? Is it okay? Yes. This is the sixth. The density of the field lines gives the magnitude of electric field. So in a region, at any region in space or at any point in space, wherever the density of lines are more, okay, then the electric field, the magnitude of electric field will also be more. At any region or at any point, if the field line is less, density of field line is less, then the magnitude will also be less in that case. So the seventh property will be, the electric field lines is always, not only sometimes, but always perpendicular to the surface of the charge. Surface of the charge. So those field lines that is being produced by the charge will always be perpendicular to the surface of the charge. So consider that this is a positive charge plus Q. These are your field lines originating from it, generated by this charge, right? Then these field lines, okay, they will be perpendicular to the surface of the charge. Are you getting that? Is it okay? Similarly for a negative charge also. If you draw for a negative charge, then the electric field lines is directed, the electric field is directed inwards. Okay. Then these lines, they will be perpendicular to the surface of the charge. Is it okay? Yes. So that is the seventh property. The eighth property would be, two electric field lines, they will never intersect each other. Two electric field lines. Duita field lines though, that is being generated by a charge, they can never intersect each other. Ito duita kita intersect na koribo. Ito duita kita intersect na koribo. Ito duita kita intersect na koribo. Is it okay? Yes. So the electric field lines do not intersect each other, or never intersect each other. So that is your eighth property. The ninth property, these electric field lines, they are repelled by a positive charge and attracted by a negative charge. Let's see the figure. The electric field lines are always repelled by a positive charge and then attracted by a negative charge. So suppose this is your positive charge here. Okay. So suppose this is a field line coming. Suppose there is a field line coming towards the positive charge, right? Then what will happen? It will be repelled by this positive charge. It was going along this direction, but it now gets repelled by this positive charge. One more electric field line coming in this direction, it will be repelled by this positive charge. Okay? But it is attracted by a negative charge. Suppose this is your negative charge. This is your field line coming in this direction. It will be attracted by a negative charge. The field line coming in this direction, it will be attracted by the negative charge. Is it okay? So this is your 9th property. The 10th property is whenever you see a parallel, straight, equally spaced field lines, then it represents uniform electric field. Let me show that to you. Up to a point, then is it clear to you? Okay, very important properties. Your J unit and all this kind of questions from based on these topics properties can come. Okay, I've seen that. So parallel, straight, equispaced means equally spaced. Okay, field lines, what happens? Represents a uniform electric field. Alright. So I'm going to draw parallel, straight, equally spaced field lines. Then this region represents uniform electric field. Suppose you want to find out the electric field at point A. You want to find out the electric field at point B here. You want to find out the electric field at this point here. Then the electric field at point A will be equal to the electric field at point B will be equal to the electric field at point C. Is it okay? So parallel, straight, equispaced field lines, they always represent a uniform electric field. The 11th property, the last property for us now. Okay. The electric field lines, we have seen that they are perpendicular to the surface of the charge, right? Here also, in number 11, the electric field lines, they are always perpendicular to the surface of the conductor. Okay? Suppose if there is a conductor, then the electric field lines, they will make 490 degrees to the surface of the conductor. Are you getting me? Yes. Suppose if there is a conductor here. Okay? Then the electric field line, they will be perpendicular to the surface of the conductor. Surface of the conductor perpendicular. Is it okay? Now they will always be perpendicular to the surface of the conductor. That is your 11th property. So these are some of the properties that you have to keep in mind regarding the electric field lines. And depending on it, okay, we can know the direction of the electric field. Alright? Okay. So once more, what is an electric field lines or electric line of force? It's a path along which a free positive charge would move if it is allowed to do so. That is the definition for electric field lines. Alright? We can highlight some of the things for this and we will go for the next topic.